So this is lecture 10 on the course Proof Complexity as a Computational Lens. So we're going to talk about the polynomial calculus proof system today. And we know that the context, what we've learned so far, is that degree lower bounds implies size lower bounds. Namely, just to repeat this, by now we're used to this. Even in the strongest form of polynomial calculus, with dual variables, but we won't have dual variables today. The lower bound on size that we can prove is exponential in the lower bound on refutation degree minus the initial degree of the polynomials squared divided by the number of variables. So what we're shooting for is this, of course, assumes that the degree of refuting the polynomial is larger than the initial polynomials, that we're using all of the polynomials so that this is not negative. Which we didn't state before, but this holds if the degree of refuting a formula is actually larger than the initial degree, which would be the case for all inputs that we're ever interested in. So since we know this, we just need to prove degree lower bounds, and we have said that we are going to be in a multilinear setting. So all our polynomials are multilinear. So any variables occur with exponent exactly 1. And then just for technical reasons, we have variable multiplication. What do I mean by this? We allowed multiplication with arbitrary polynomials before. Now, today, our multiplication rule is going to be that if I have derived the polynomial p, I can multiply it by a single variable x. This doesn't really change anything. This is just for simplicity. So what we concluded last time by saying, so we just need to prove degree lower bounds now. And last time we concluded by talking about pseudo-reduction operators, or R operators. That is a linear operator on polynomials that satisfies 3 properties. It's linear, and for any input polynomial f, R maps f to the 0 polynomial. For any term, if the degree of the term is strictly less than capital D, which is a parameter, so we're building a degree capital D pseudo-reduction operator. For any term that has strictly smaller degree than this, it should hold that if I multiply the term t by x and apply R, that should be the same thing as first reduce t, and then multiply by x, and then reduce again. This is, by the way, how it would work if this was a real reduction operator. We'll get to that in a moment. The third property we want is that the field identity 1 doesn't map to the 0 polynomial. If we can build a pseudo-reduction operator with these 3 properties, then we saw last time that this shows that the degree of refuting the set of polynomials p is strictly larger than d. So, and what we have done before and what we will talk about briefly today, we've talked about these generalized clause variable incidence graphs. What we are going to, and we've proven that if these generalized clause variable incidence graphs are good enough expanders, then we get degree lower bounds. So what we'll use these graphs for is just to build R operators. So the name of the game today is to build R operators. So we need just to quickly review some algebra for this. So let's start talking about admissible orderings on polynomials, or rather on monomials. Just as a quick comment, there's a notion of admissible orderings in algebra. We are doing a special case of admissible orderings. That is what we want, what we need for our result. If you read an algebra textbook, the definition is slightly less restricted. So it's a total order on monomials, and it will satisfy that if a monomial M2 has larger degree than M1, then M1 is strictly smaller than M2 with respect to the order. So it's this curly less than. Okay? So our admissible orders will always respect degree. This need not be the case in general in an algebra text. Today we'll insist on it for simplicity. Then we also say that if it is the case, if I multiply by some monomial M, which has the property, and this condition is because of multilinearity, that it doesn't occur in M1 or M2. I multiply by a monomial M that does not occur in M1 or M2. And if it holds that M1 is less than M2, then multiplying by M doesn't change this. Okay, so any ordering, so now we just fix an order on monomials, and anything that satisfies these properties we'll refer to as an admissible ordering. And we'll use the less than equal to obviously mean that M1 is strictly less than M2 or is the same. We also have terms, and remember that a term is just a monomial multiplied by a field element, so terms will inherit this order. So when we talk about ordering terms, we just look at, oh, this is a term over which monomial, and then we order the monomials. And we will, for today, just for concreteness, fix degree lexicographic. So again, degree wins. So for instance, we have x2 times x3 times x5 is less than x1 times x2 times x3 times x4. This is a larger monomial because it has a larger degree. And now if we look at x2, x3, x5, and we compare it to x2, x3, x4, then by lexicographic sorting, x2 is the same, x3 is the same, but x4 is smaller than x5. Okay. So the leading term, now we have a total sorting on all monomials. And this means that writing a polynomial as a sum of terms, we can pick out the largest term. With respect to this order. So from now on, we'll think of polynomials as basically whenever you give me a polynomial, I'll be interested in the leading term and the rest. Now that we have this, we can consider any I, which is an ideal in the polynomial ring. And for all of today, let's stay in a multilinear setting. Okay, so we're in a polynomial ring, except we don't have higher powers. Let I be any ideal. That is, it's a subring. It's closed under addition. It's closed under multiplication. It's also closed under multiplication by any other polynomial. Okay. We say that a term T is reducible modulo the ideal I if there exists a polynomial Q such that the leading term of Q is T. And otherwise, we say that the term is irreducible. Does this make sense? And note that these notions of reducible and irreducible, they only make sense thanks to the fact that we have leading terms, which is thanks to the fact that we have defined an order. So now we're going to need a few facts. The first fact is that if I pick any polynomial P, then I can write it as P equals Q plus R, where Q is in the ideal, and R is a sum of irreducible terms. And just to save typing, let me call it irreducibles. Okay. This should not be so hard to see. Any polynomial can be written as something in Q plus a sum of irreducibles. Just by induction, let's start with the leading term in P. If there's something in Q with the same leading term, I subtract it and then argue by induction. If it turns out that the leading term is irreducible, then it will be part of R, and then again I do by induction over smaller terms. So you agree that I can do this? But the point is that, in fact, this representation is unique. And this is super important. This is something that we will use. And uniqueness is not so hard to prove. Like, suppose that P is Q1 plus R1. And suppose that it's also Q2 plus R2. Then I just rewrite R1 minus R2 to be Q2 minus Q1. Now, if these are distinct, then there's a leading term over here, which is apparently in the ideal, because Q2 is in the ideal, Q1 is in the ideal. Definitely their difference is in the ideal. But that means that one of the terms over here is apparently reducible there, contrary to assumption. So we're going to use heavily from now on that once we fix our polynomial ring, once we fix our so-called degree lexicographic order, any polynomial I can write. Once I fix the ideal, I have any polynomial defined uniquely as a Q plus an R. The analogy, if you see this for the first time, think about counting modulo. Basically what I'm saying here, this would be the claim that if I'm counting mod 5, then any integer can be written uniquely as a remainder between 0 and 4 plus a multiple of 5. That's all I'm saying. And then I'm saying, and the remainder mod 5 is unique. It can't be both 2 and 3. It will be, one of them, or maybe 4 or maybe 1. Okay, but now that I have this, we can define the reduction operator over, with respect to the ideal I, of the polynomial P. That's simply the remainder R. Again, if I'm working mod 5, and this is 17, then the reduction of 17 mod 5 would be 2. And the point is that once you've defined an invisible ordering, you can do the same for any monomial. So for a set of polynomials, fancy style P, I'll write P within angle brackets to be the ideal generated by the polynomials in P. What is this? That is all polynomials Q that can be written, all polynomials Q, let me write it this way, all polynomials Qi times Pi, for Q being any polynomial and Pi is in P. Okay? This is the ideal generated by the polynomials P. And now one thing that we're going to use is that in a multilinear setting, the following holds. Let me maybe write it in this way. So look at the reduction operator modulo P, and suppose I reduce a polynomial Q. Suppose this reduction operator yields a 0, then obviously this is the same thing as saying that Q is in fact in the polynomial generated by the P's. And this is not so hard to see, that if Q is a polynomial that is generated by the P's, then anything that zeroes out all the P's, anything that satisfies all the P's, have to satisfy Q. Hopefully you're buying this. Now, what we're going to use, what I'm not going to prove to you, but maybe we'll put it on a problem set. I haven't decided that. All of these are in fact equivalences. Here I'm using multilinearity. So what can go wrong? Like, why isn't this true in general? Well, suppose that P is generated by, I don't know, x squared minus 2x plus 1. Okay. Then I claim, so if we're in a null multilinear setting, if you stare at this for a while, you realize that this implies x minus 1. Because this is just x minus 1 squared. Okay, so P implies x minus 1. Is it true that x minus 1 is in the general polynomial ideal generated by this? No, right? Because anything generated from this ideal will contain x minus 1 squared and not x minus 1. But that's the only thing that can go wrong. If you multilinearize, then you have an equivalence. I'm not going to prove this, but we're going to use it. So I want two more obvious facts.
Jakob?
Yes.
So in general, like you say, if you multilinearize, it works. But so in general, if you consider P to be an ideal that's reduced, it would always work?
Sorry, I did not quite parse the question.
Oh, sorry. Yeah. You, with your example, like it fails also basically because P is not reduced, right? Your ideal is not reduced.
I don't know what we mean by reduced. What I'm saying is that if you in a multilinear setting, then this polynomial would actually reduce to be minus x plus 1. I'm not sure what we mean by a reduced ideal.
Oh, well, then it doesn't matter. That's fine. Okay.
But all I'm saying, we're going to be in a multilinear setting. So we're going to use, like, one fact that we're going to use heavily is the unique representation. That I can, once I fix the ideal, any polynomial reduces to the part that is inside the ideal and the smallest remainder outside. And then I will use that this reduction operator, modulo an ideal, reduces Q to 0 precisely if Q lies in the ideal, which is precisely if P implies Q. And I can go back and forth. And this is going to be a little bit convenient for us. Two more obvious facts that we're going to use is suppose that I1 is a smaller ideal than I2. And suppose that I start with a polynomial P prime, that I reduce modulo the smaller ideal, and then I multiply by P, and then I reduce modulo the larger ideal. Then this is the same as just multiplying P and P prime and reducing modulo the larger ideal. Okay, what are we saying? This is sort of proof. This is basically saying So over here, you have something like B mod 15, say, times A, and then you take all of this, mod 5. Okay, this is like the left-hand side, and I'm saying, well, that's the same thing as just taking A times B mod 5. That's all I'm saying. Like if you modulo a smaller ideal first, and then multiply, and then modulo a larger ideal, it's the same thing as just do the multiplication in the larger ideal and then reduce. Are you happy with this? Hopefully you're happy with this. The final very obvious claim that we're going to use is suppose that T is irreducible, mod I, and suppose that rho is any partial truth value assignment such that T restricted by rho is not 0. So rho does not satisfy T. Then I claim that T restricted by rho is clearly also irreducible. Right? And the proof is basically, well, suppose that this was not irreducible, that there is a Q that has the leading term this, then basically I just multiply by the variables in rho and I will get the polynomial that has leading term this. So if I already have irreducible terms, and if I hit these irreducible terms by any partial truth value assignment, and I shrink it, it remains irreducible. Are we happy with this so far? Or so once we have this set up, what we're going to do now is, okay, so recall now that we have P, we're writing it as Q union and M. We're dividing the set of polynomials up into a special set Q plus a bunch of sets P1 up to Pm, which we think about the vertices on the left-hand side transistile U of a graph. Similarly, V is union of a bunch of Vj's. From I goes from 1 to M. And there's an edge between P and V, Pi and Vj, precisely if any variable in Pi occurs in Vj. So we build this kind of graph, right? We look at the set of polynomials, we group them according to the combinatorial structure and group the variables in some way also, which we did last time, like somehow with respect to wholes for the pigeonhole principle, for instance. And then we get this graph. Then our idea is that, so what, like, let's see what's going to happen today. So I want to tell you a high-level idea, that's one. Then I want to explain to you that we already did this for resolution, and I will try to see if you can see the parallels, and then we'll try to do it for polynomial patterns. So the high-level idea is that for every polynomial, P, we define a set of associated polynomials, actually a bunch of capital PIs, which we refer to as the support. Once we have this, we will define the reduction operator, the pseudo-reduction operator, to be honest polynomial reduction modulo all the polynomials in the support of P, and we'll always throw in the Q set, because the Q is somehow telling us about well-behaved truth value assignments. So for every polynomial p, we'll somehow find a somewhat large but not too large set of the input formula, and our R operators will reduce p modulo this. And now we want to show two things. That if the degree of p is less equal, not too large, spoiler alert, if it's less equal d, I guess, then we want to argue that reducing p modulo the support and throw in the Q set, R maps p to 0 when reducing modulo this polynomial. But the support is not too large either. So since the degree was not too large, the support is not too large. So, in fact, support of P union Q is satisfiable. And if we can somehow pull this off, then we will be done, because any polynomial that is derivable in small degree is implied by this set of polynomials, which is a small enough set to be satisfiable, so P can't be contradiction. So what is not clear, perhaps, but what I want to make explicit now is that we did exactly this, or we did something extremely close to this for resolution when we talked about the Benson-Wigderson size-width relation. I don't know if you see this, so let me try to explain what we did. Well, looking back for resolution, what did we do? We actually had this UV graph, and we defined what we called the S support of a clause. And then we showed that, if you remember, by induction over the derivation, we showed that the clauses in the support and throwing in these Q clauses, they actually implied C. Remember? Okay, but again, in our language, if we look at these as polynomials, then let's just point out that what we're saying here is just that C is, in the ideal, generated by the support and the Q set, right? We're just using this equivalence. The key technical step, if you remember, was the key technical step when we had C1 and C2 and they derived C. Then the problem is we didn't know anything about the support of C, but we knew that the support of C1 union the support of C2 union Q implied C. Just by induction, we knew for C1 the support implies it, for C2 the support implies it. This is a sound rule. Taking the union of the supports, everything is fine. But the problem was, I mean, this was not the support of C, so it was the wrong set, and it was also potentially slightly too large, but not more than twice as large as we would like. So the key technical step was the following. Basically, rewriting what we did, we said that, well, take any set S that is contained in the support, that contains the support of C, and fancy style S is, again, not too large. And we said, suppose that for this fancy style S, we have S union Q implied C. Remember, this is exactly the setting we had, right? And then we proved, in fact, that, well, if that is the case, then S intersect support S of C. And since support is actually inside, we can even remove the intersection. Implies C. How did we go from this large set S implying C to just the support implying C? How did we do this? Well, we said if there's something in here that isn't in here, then S was not too large. So actually, the only reason all of fancy style S wasn't inside the support was that there was some unique neighbor outside. And then we peeled off the unique neighbors one by one until we shrunk it down to set this size. How were we able to peel? Because we were playing the game. Okay, and note that this means that we actually had an R operator for resolution. So for resolution, we basically had the following condition. A condition 2 prime that said basically if the number of variables in a polynomial is smaller than D, then good things. Then the R operator is well behaved. This is basically what we proved for resolution already. And as we talked about, why isn't this good enough for us now? Now we need to do the same, but to talk about the degree of P. And note that clearly if the number of variables in P is very small, then the degree cannot be large, but we can have a low degree polynomial that contains lots of variables. And this is what we need to do. Okay, so now is your last chance to ask about irreducible or reducible terms because I'm erasing the definitions. Any questions up to this point about our general direction of travel, what we're trying to do and why? Or is it all clear as mud? Okay, actually, let me erase that also. So what I tried to explain to you so far, successfully or not, is that we already did this for resolution by looking at the combinatorial structure and this graph structure. For resolution, we looked at clauses, we associated subformulas with clauses, and then we proved that these subformulas implied the clauses in question. Now we want to do all of this for polynomials, but we're going to need to work harder because we're trying to prove stronger things. For all we needed to do for resolution was to argue that as long as the variable set involved is not too large, then things work. And now the variable sets can be very large, but we know that the polynomials have small degree. Okay, so from now on, let's fix for P a graph with polynomial sets on the left-hand side, variable sets on the right-hand side, the special set Q floating somewhere outside the graph. And let's suppose that this is that sets of size at most S expand by a factor delta, except for positive and additive like psi. And when we're looking at the boundary expansion, this is with respect to playing the game on the Q set. So we're assuming that this graph is a PC expander. And in fact, I'm going to assume more from now on. I'm just going to fix, because it gets annoying, let's say that we have a true expander, that this is 0. Basically, nothing happens in the proof. We just carry this additive constant around all the time. So I'm going to cheat and do the proof only for true expanders. But if you get that proof, then to do the slightly more general case, you just carry this constant around all the time. So now we will do the same thing as for resolution. What did we do for resolution? We defined a neighborhood of clauses. So now we need to define neighborhood of terms. So once we have this graph, this is sort of suppose that we add an extra ghost vertex that contains only the term t. What kind of neighbors would it have? Well, it would have as neighbors all the v that intersect it, right? Bars t intersect v. So once I've fixed the graph, I can look at any term and I just let's look at all the right-hand side vertices that contain any variable that occurs in t. I'm going to call that the neighborhood of t, just as we did for resolution. And if p is a general polynomial, then the neighborhood of the polynomial is just the union of the neighborhood of the terms. Hopefully nothing strange so far. The next notion we had was these things being contained. So look at a subset of vertices u prime in U, and look at another subset of vertices v prime on the left. Then we say that u prime is S v prime contained if two things hold. I want to say that u prime is not too large. That's the first parameter. U prime has size at most S, and the boundary of u prime with respect to the good edges, all of them lie inside v prime. This is exactly the same that we did for resolution. Okay. And now I want to somehow say, is u prime, is it a set of polynomials that could maybe have been used to derive a polynomial for which the leading term is t? That's the intuition. I mean, at the end of the day, all we have are mathematical definitions, but maybe my intuition for the next definition is, let's see if u prime is potentially a set of polynomials which could have been used to derive a polynomial with leading term t. So we're going to do exactly the same definition. We're going, as for resolution, we're going to say that u is, well, S and T contained. Actually, this is not a definition, I'm just writing it down. So u prime is S and T contained if, just by definition, if the size is at most S, and note that the boundary of u prime, these are sort of all the, here I pick up all the variables that if a variable is in the boundary, that means that it would have been hard to cancel it. And any such variables, they should be in the neighborhood of t. And now I just define, still exactly as for resolution, we define the support, the S support of a term t, to be the union of all S and T contained sets. Contained left sets u prime. So if u prime is S and T contained, then I'm thinking, yeah, it could have been used to derive a polynomial with leading term t. Let's take the union. Then surely I'm picking up everything that could be involved in the derivation of a polynomial with leading term t. Okay. So far, we're doing exactly the same thing as for resolution. Note, by the way, that we're just working on the graph now. And we're going to keep working on the graph for a few more minutes. We're only doing things, we're not using the game on the edges or anything. We're just arguing structurally about graphs and about boundaries. So our definition now is going to be, so maybe our pseudo-reduction operator, let me put it over here. We are going to reduce the term t by looking at the ideal generated by the support of t, union q, and reduce t modulo that ideal. And now I'm just going to argue that if this graph is an expander, then this is a Razborov pseudo-reduction operator, and we get a degree lower bound. Okay. Note that this is an R operator is only defined on terms. We need to define it on polynomials. Let's extend it by linearity. I just define it on terms and then extend it by linearity. So then linearity is for free, and we only need to look at the other properties. So now with this definition, the key technical lemma, again, trying to see the parallel to resolution, what we need to prove in order to be able to go home is the following. Suppose I take a set S that is actually strictly larger than the support, but not too large. What is not too large? Well, not too large is going to be the expansion guarantee. So note that S is all the left vertex sets of size at most S are expanding. That S is what I'm going to carry with me. So fancy style S should be of size at most S, and it contains the support. Then I want to prove the following. So look at what is RT. Well, I know what RT is. RT is reduction modulo the support of T union Q of T. So this is our pseudo-reduction operator. It is defined in terms of an honest polynomial reduction operator over the support of T union Q. Here S now is a larger set, much larger set potentially, but not too large. The magic property that I want is if I instead reduce over the much larger ideal fancy style S union Q, then I get the same result. So this is all we need to do, but it's going to take us a while. Okay, so let's. I was thinking now that maybe I don't know about you, so maybe this is a good time to stop and think about questions, or maybe in 5 minutes from now is a good time to stop and ask questions. My plan, absent other input from the audience, is as follows. This is going to get highly technical. So before just launching into a lot of fiddling with polynomial reduction operators, I want to state the key lemma somewhat more formally. And then I want to hand wave a proof of why we have an R operator, except that I'm going to try to cheat you on some details. So your task is to figure out where I'm cheating you. But I'm not going to cheat too bad. Like morally, I'm cheating for a greater good. So the overall outline of my proof will be sound. And then we'll say, yeah, but you're sweeping details under the rug. And I say, sure. Yes, you're right. And we're going to need maybe 1 hour, 1.5 hours to figure out these details. But except for that, we kind of know where we're going. Okay, so my plan is to give a high-level, almost valid proof with some technical details, and then we'll fill in the missing technical details. But just to say that this is the R operator that we will use, so we just need to prove that this is a pseudo-reduction operator in the sense of Razborov. Are there questions at this point before I launch into the high-level proof? You're just radiating pure happiness, all of you. Okay, fantastic. I love that.
Could you repeat again what was the intuition for the definition of the support? Like, how could one come up with this?
The idea, again, what did we do for resolution? We're arguing against an enemy that is a resolution proof or a polynomial calculus proof. But the limitation of the enemy is low degree, somewhat low degree, or somewhat low width. So we're trying to lie in such a way that a low degree resolution person or a low degree polynomial calculus reasoning engine cannot detect that we're lying. So what we did for resolution was basically we said for every clause we looked at it, and we identified a large part of the graph. We identified a large part of the formula which contained clauses that seemed to be useful for deriving the clause C. And then we proved by induction over the derivation that it was indeed true that C always was always implied by this somewhat large set of clauses. And then we proved that since the clause set was not too large, this meant that it was satisfiable, so anything implied by it is also satisfiable. And so actually the argument that we were faking against the resolution prover is we were sort of saying, well, look, I'm showing you how a set of clauses that derives, that implies anything you can derive, but contradiction is not derived. So I was arguing to the resolution prover that your formula is in fact satisfiable, and in low width it looked like it was. So here for polynomial calculus, we are in a similar way for any polynomial. Now one thing that is a little bit clear, I throw away in structural information about the polynomial. I just focus on the leading term. So this is a first example where the intuition is slightly off. Let's just ignore this. So I'm looking at a polynomial, I'm looking at the leading term, and now I'm identifying a somewhat large set of polynomial constraints in the input that could have been used to derive this. And thanks to this, I'm now saying that the way I'm proving to a resolution prover, to a polynomial calculus prover, that the formula requires high degree is to say that, well, I actually show me your derivation, and I will reduce everything modulo the polynomial ideal generated by your input. Because a pseudo-reduction operator is exactly what a real polynomial reduction operator would do. So the Razborov properties of an R operator is precisely what a reduction modulo an ideal does. And so we're going to prove by induction over the polynomial calculus derivation that in every single step, if I reduced correctly before, then I'm reducing correctly for the new polynomial. Except this can't be true because we know that the polynomial in fact implies contradiction. So one is in the ideal, but the point is you cannot see this in low degree. So as long as both we and the adversary are operating in low degree polynomial calculus, the adversary cannot tell that we don't present a real true polynomial ideal reduction operator. And then we prove that one, according to this fake ideal, one does not lie in this fake ideal. And again, how do I pick the set of polynomials? I want to pick it somewhat large. I want to pick it so that it seems related to having derived the polynomial. And this is this containedness property, that there are basically a set being SNT contained means that the only variables in U prime that could be in the boundary are those that are in this term. Anything else must have cancelled, and therefore it cannot be in the boundary. And then I just pick that set as large as I can, and I say a pair that it will work. I'm not terribly sure whether that was a good answer. I'm not even sure if I answered your question.
Yeah, I did answer my question. Yeah, so we should think of the support as like the set of polynomials that could have been used to derive your.
That is one way to. I mean, at the end of the day, intuition is one thing. The only thing that exists is the math that we're going to do now. But if this intuition is helpful for you, then.
Yeah. Okay. That was helpful. Thanks.
Okay. So following Alekhnovich and Razborov, I think they call it the heart of the proof lemma, which is a kind of a nice name. So let's talk about the heart of the proof lemma. The heart of the proof lemma says, let T be a term, and suppose that U contains the support of T, but is not too large. Namely, it has size at most S. So in particular, this vertex set has expansion guarantees. Then what I want to prove is, as I just wrote, that reducing modulo all the polynomials in U prime plus Q. Note that I'm overloading a little bit. This is a collection of sets of polynomials. So I'm sort of unpacking two unions here. I hope you're fine with that. So reducing modulo the polynomial ideal generated by all the polynomials in Q and all the polynomials in all the PIs that live in U prime is the same as reducing modulo the support of T union Q, which is exactly how the R operator is defined. So what's the idea for proving this? Let's reduce T modulo this larger ideal. Let's see what we get. Okay, so we're going to get that T is equal to first some polynomials AI times PI, where PI lives in the support, or it could live in Q. Okay. Then we also get some Q, Bj times Qj, Bj times Qj for Qj living in U prime minus the support union Q. Okay, because we know that we can write T as some polynomial living in this ideal. This is the ideal generated by U prime in Q. And then there are some irreducible terms. Let me write them as, so RK is now terms. And the RK are irreducible mod U prime union Q. So basically what I would like to do now is, suppose I could just somehow magically get rid of these guys. Then I would have written T as living inside this ideal plus some irreducible terms that are irreducible already modulo a much larger ideal. So clearly the RK, if they are irreducible modulo this larger ideal, they're definitely irreducible over here, right? So I just somehow would like to say that actually you're not using these guys. How would I do this? Well, note that the PI sets in U prime that are not in the support, I know that they have unique neighbors Vj outside of the neighborhood of T. That's why they're not in the support. So what I'm going to do, I'm going to look at all the, let me call them P prime, all the sets of polynomials that are outside of the support. So they live in U prime minus the support of T. I know that since they are not in the support, I can find good edges. P prime, B prime. By this peeling argument that we've done before. And now, note, what can I say about V prime? All of these V primes, they're not going to be in the neighborhood of T, right? And in fact, they're not even going to be in the neighborhood of the support. Because if they were in the neighborhood of the support, they wouldn't be unique neighbors. So I know whenever I set variables in these V primes, I will affect these guys and potentially these guys, but never these guys. Are you with me? This is because it's again, V prime is a unique neighbor. Unique neighbor, in fact, in U prime of V prime. So what I will do then is basically, since I can win the game, I will find a row that, okay, let me cheat a little bit now, except I wasn't supposed to tell you I was cheating. So I will find a row. This is the move that we would play in the edge game. And the way you can think about this is that row of P prime, row satisfies P prime, and row satisfies anything in Q that it touches. This is the same thing as saying that if I take this filtering set Q and hit it with row, then I get back a subset of Q. Okay, suppose, now let's see what happens. T is completely unchanged because row doesn't set any variables in T. Also, row doesn't set any variables in P. Maybe it sets some variable in AI. I don't care. Because this is just, I mean, AI restricted by row, this still lives over in this ideal. And note that in Q, some of the Qs maybe just vanish, and the other ones I will pick up AI restricted by row. Since I'm satisfying the PIs, I am in fact getting rid of all of these guys. Maybe I need to do this. I need to do the peeling argument over and over again. But I'll do this, like I'll peel away until I get rid of all of these. Okay? What happened over here? Well, here is the part where I actually don't have control. So it's something, you know, here, wild things might have happened. But now I claim that I'm happy once I have this. It's like, yay, we actually have that the original, I claim now that if we can do this, then I've proven to you that the original RKs are in fact what I got over here. How can I argue this? How can I claim this? Well, note first that the RKs are irreducible modulo the larger ideal, so clearly irreducible modulo the smaller one. Okay? And the same thing holds for RK over delta. So anything I see here is irreducible for both ideals. And note that after the restriction, I've actually written T as something that is irreducible over this ideal. Plus note that this part definitely lives inside this ideal. So this is a little bit interesting now. Inside the larger ideal, I've written T in two different ways. Right? I started writing it in only black. And then I hit it with the green restriction that removed all of this and potentially shrunk all these terms. And when the dust settled, we realized that, well, we haven't touched the Qs, we haven't touched the support, and these are still irreducible. I mean, if they were irreducible modulo this large ideal already before the restriction, then definitely they're irreducible after the restriction. But that means that I've written the term T as a polynomial in this ideal plus irreducible terms in two different ways. That's not possible. So actually, it turns out that rho didn't do anything here. And this must have been the reduction already. I mean, I get the same reduction over here and over here, which is to say that indeed the two reductions are the same. Questions about this? So the key step, again, here I will use the peeling argument, and this will use expansion and unique neighbors in the graph. Okay, if you grant me this, let's just see. So once we have this, we can do the main theorem, which says the following, that suppose that the UVQ graph is an S delta, and let me fix it to 0, Q PC expander. And let me say that the overlap is L. Then I claim that R, let me actually, okay. R defined in this way is a degree D pseudo-reduction operator for D being this expression that we vaguely recognize by now, expansion factor times expansion size guarantee divided by 2 plus times the overlap. Okay. Let me keep hand waving how we would prove this. And I'm doing, so there are some small annoying details that we are ignoring, but except for this, we are essentially doing the full proof now. We'll have to talk a little bit about how to fix the details. It's going to take a while, but we're finally getting to the heart of the algebraic argument. So we need to prove three things. The first property is for f in P, Rf is 0. This requires more work than for in the resolution case, but basically, for what we did for resolution is we said, well, look at an axiom. That axiom, whatever pi contains that axiom clause must be in the support of F. Because if it isn't, we basically said we fix we fixed a neighbor of F that wasn't in the support, and then we argued that, well, in that case, it wasn't a good edge. So this is going to require some work, but basically, okay, let me maybe say it follows because it will be true that F will be contained in the support of the leading term of F. This will require an argument, but it won't be too bad. Okay, so this is the base case. Sorry. So this is property 1. Let me now do property 3. We're now going to argue about what happens when the R operator is applied to 1. Note that I claim that 1 is actually a low degree term. You agree that 1 has pretty low degree. Okay. But then we will argue, just for resolution, we said that not too wide clauses have small support. So we will have a general theorem saying that low degree terms have small support. This is a low degree term, so hence this set is small. So hence, the support of 1 union Q is satisfiable. It's satisfiable, let me just rewrite this. This is actually an equivalence. It is satisfiable if and only if 1 doesn't lie in that ideal. Are you with me? I mean, this is just rewriting. This is the equivalence. But now, if 1 is not in this ideal, then what I can say that R of 1 is by definition the honest reduction modulo the support of 1 union Q of 1. I'm not exactly sure what this is, but I know definitely that it's not 0, because the only way it could be 0 is that 1 would be living inside this ideal, which it can't do because this is an ideal generated by a satisfiable bunch of polynomials. The tricky part is going to be what happens at multiplication. So we need to prove that R of xt for a low degree term t is equal to R of x times R of t. Okay. Maybe this is a good place to stop and say, do you agree with, like, are you kind of happy with the proof sketch up to this point? I mean, I've given you the honest definition of the R operator. I've given you the honest statement of the heart of the proof lemma, and I've given you something that is morally extremely close to a proof. This is essentially the proof. We just have to flesh out the details, but this will be the proof. And we're just going to use that, again, by row, we're able to get rid of polynomials that lie outside the support without hurting the filtering set. And clearly, restricting irreducible terms can only make them even more irreducible. And then once we're done and the dust settles, we say, oh, we have 2 different representations of t, but that's impossible because writing t as something inside this ideal plus irreducibles, that's unique. So these 2 different representations with and without the rows, where one lives in here and the other one lives in here, they have to be the same. Okay? This was also honestly stated. And then we just need to prove that, okay, f lies in the support generated by its leading term. Then clearly, if I try to reduce f modulo this ideal, well, if I reduce p modulo an ideal that contains p, then it reduces to 0. That is clear. The R of 1 is, by definition, reducing 1 modulo the ideal generated by the support of 1 union q. And if I can argue that this is a satisfiable set of polynomials, then I'm done, because then 1 is not inside the set of polynomials. And so the tricky thing that we have left is, okay, and sort of morally, if you take a step back and just think of what happened in the R operator theorem, since we defined a linear operator, doing addition steps, linear combination steps in the polynomial calculus proofs was always without loss of, without any problem by definition. But the problem is this property we need when the derivation does multiplications, and we want to argue that even in a multiplicative setting, it looks like R is actually reducing modulo some kind of fake polynomial ideal. This is where we need to do serious stitching. We're going to reduce modulo tons of different ideals. And we have to argue that even when we're reducing modulo these very, very different ideals, it's all the same, right? That's where we need to stitch. And this is exactly what the heart of the proof lemma does. It allows us to, once we have a support, we can enlarge it in all kinds of different ways, and still the reduction is still the same. So like, as long as we don't go too far outside of the support, we can stitch. Any questions at this point before I launch into a proof of this? So let's think about it. Let's just see how would we prove this. Okay, so this is what I need to prove. Let me start by working on the right-hand side. This is just by expanding out. This is x times whatever this polynomial is. T prime in R of t, t prime. Right? This is just by expanding it out. Now, by linearity, this is going to be taking R of xt, summing over all the t primes. I'm just saying this. So first, let me actually move x inside here so that it's even clearer. And then I just say by linearity, R applied on a sum is just the sum of the R's. Are we happy with this? Okay, so now what is this? Well, this we know by definition. I just need to, what is R applied to xt prime? Well, that is the honest reduction modulo the support of xt prime union q of xt prime, right? And now, here comes the magic. So I claim that essentially by the heart of the proof lemma, we will need a little bit more, but the heart of the proof lemma is almost what we need. That I can zoom out and actually I can plug in x times t, where t is the original term. Note that here I'm reducing, every term is reduced modulo a separate ideal. And I say, actually, use this ideal for all of them. This is clearly like some serious magic is happening here. This requires an argument. This is like super false in general. So we need to explain why we should be able to do this. But let's not worry too much about this. then suppose that this works. Then by linearity again, let me reduce modulo the support of xt union q t prime in R of t x t prime. This is just by linearity because standard polynomial reduction is superlinear. Okay. So let me actually pull x out, put it here. Are you agree with me that I can do this? What do we have here? Well, this is just R of t, right? So now we get R sup xt union q x times RT. And now we're almost done. Not quite. Let's keep working on this. What is this? This is actually the honest reduction mod support of T union Q T. Okay, but now if you remember, now look at this and you realize that here I'm taking the support of T. I'm taking all the polynomials that have all their unique neighbors inside the neighborhood of T. Here I'm taking all polynomials that have their unique neighbors inside xt. That's a larger set. Okay? So this polynomial ideal is larger than this one. So now we're in this setting where I'm saying this was this, you know, if I do b mod 15 and then take times a and mod 5, then I can just multiply everything and then take mod the larger ideal, because this ideal is contained in this one, right? So this is like, this is I1. Is contained in I2, which is the support of xt union q. I should have written this in a different color maybe. The point is, again, this is I1, it's contained in I2, so I can just multiply, instead of first taking t, reducing it, multiplying by x, reducing it again. Let me do the multiplication first, xt, and then reduce modulo the larger ideal, which is sup xt union q. And now what do I have here? Well, this is the term xt, reduced modulo the support of xt. So this is actually how the pseudo-reduction operator is defined. Where did I give me 1 second? Just to point out that the only place, we can talk about this, but the only place where magic happened was here. Everything else we did was just patiently unpacking, using linearity to pack and unpack, and then we were using this definition over and over again, but nothing else. We just very, very carefully used the definition and used linearity, and then suddenly here something magic happened that we couldn't explain. But if I can just prove this lemma to you, basically what is left now? I need to prove this lemma to you. I need to prove that low-degree terms, basically low-degree terms, have satisfiable support. And I need to prove that for axioms, they lie in their own support. if I can do this, and proving this big orange box is incidentally, it's going to use the heart of the proof lemma plus some other stuff. Then we're actually done. So I think except for the orange stuff, there's no cheating left on the board. And so this might be a good place to, so what we need to do now is just to figure out the orange stuff. And just to say that this first part, that small support is satisfiable, we actually did that for resolution. I don't know if you remember, we had this peeling argument. We took a small set. It was small enough to be expanding. So we found like, we found a bunch of edges. If you remember this picture, we started with a large set, and then we found one unique neighbor, and then we peeled. And we found, for the first set, we found an edge that was a unique neighbor of this guy, but was not connected to the others in any other way. And then we kept peeling our onion and found edges like this. And then we argued satisfiability by first we just took any assignment that satisfied the filtering set Q, and we played on this edge, and then we satisfied this. And then we played on this edge and satisfied this and satisfied Q, and didn't affect the truth value assignment to this because these variables didn't appear over here. And then we played on this edge and satisfied Q on this and didn't affect these because these polynomials didn't contain this variable. And then we just kept peeling. So this was actually, I don't think we're going to do this because it's exactly the same argument. So I actually kind of, if I can prove to you that low degree terms have small support, then we're going to be done. And that part is almost, it's only arguing about the graph. It doesn't care too much about the edges. What we do need to argue is about the axioms, and we do need to argue the stitching. Any questions before we take a break? Then let's take a break. So we're back after the break, and we've tried to argue, we've done proof by intimidation, if nothing else. And if we can prove the heart of the proof lemma, then we should be basically done. What's the heart of the proof lemma? That if T is any term, and if U prime is any set of left-hand side vertices that is larger than the support, but not too large, it's smaller equal the expansion size guarantee, then I get the same result when I do an honest polynomial reduction for T, whether I reduce modulo its support or reducing modulo this much larger set U prime. This is really the main difficulty. And then we noted there are some technicalities that we need to deal with, but they all pale in comparison to this. This is the main challenge. As some of the audience noted, well, the main challenge in order to parse this lemma is what the heck is support. So let's recap. You just somehow have to write these down on paper, or let me try to keep this part of the board without erasing it for as long as I can. There are two key definitions. So again, we have this graph with P1, P2, P3, P4, etc. And then we have Q sort of floating down here. We have V1, V2, V3, V4, and maybe V5. And then we have a we say that something is SV prime contained. So let's suppose that V prime is these two guys. Then we will say that this set is SV prime contained if, firstly, the number of vertices here is less equal S. That's the first condition. The second condition is look at all the edges here. Okay, so let's start drawing some edges, and let's suppose all edges are good, just for simplicity. Let this be an edge, let this be an edge. Something like this. No, this is not. Okay, maybe this also. Okay. The question is, what would it take for this green set to be SV prime contained? So firstly, the number of vertices here should not be too large. And then you say, let's identify all the unique neighbors. Okay, what are the unique neighbors here? V1 is a unique neighbor. It's only connected to P1. It's also connected to P4, but P4 is outside of our set. So it's unique. V2 is also unique. It's connected only to P2. So we're saying that any such unique neighbors have to lie inside V prime. So now we see V3. No, it's not unique. It has a neighbor from both of these guys. V4 is also not unique. It's a visual illusion that V5 is unique, but you all see that this is not the case because there's an edge here. Okay. So this green guy is an SV prime contained set. Okay, this is this definition. This is a key definition. And now, what is the support? Well, now let's take term T. Let's look at the variables in this term. Okay, and suppose that the variables in T, they are mentioned in here, maybe, and here, and here. Okay. Then we say that U prime is S neighborhood of T contained if, again, it's not too large, and all the unique neighbors are orange neighbors. They are neighbors of T. Because the unique neighbors are things that these are variables that we cannot explain away. There is no way of sort of canceling these variables, but they are in T, so that's fine. Okay. And now we say that the support of T is just look at all S neighborhood of T contained sets and take their union. That's the support. Okay, two easy observations, but it's good to keep them in mind. Suppose that V prime is contained in V double prime, then anything that is SV single prime contained is clearly SV double prime contained. Like increasing the right-hand side set can only make more things contained. It follows from this immediately, and this is something that we will use heavily. Suppose that T, the variables of T are contained in the variables of T prime, and let's look at the supports. Then clearly T prime has at least as large a support as T. Are we happy with this? And now we're supposing, now if you remember, we had this magical thing saying that this we did already for resolution. Suppose that this graph is an S delta 0 Q PC expander. Then, and suppose also that V prime has size at most delta times S over 2. Then every S V prime contained set is in fact S half V prime contained. Remember we had this lemma last time, so what happened? Well, by expansion, let me do this extremely quickly. by expansion, we know that the boundary of u prime is somewhat large in terms of u prime. This is a lower bound. So the by expansion, the boundary of u is actually somewhat large. This gives a lower bound. But we also have an upper bound, right? Because we know that the boundary, by definition, I mean, so u prime is an, okay, so I should have said this maybe, u prime is an S V prime contained set. This is sort of the interesting setting. So since it is small, it is expanding, but it's contained. So we know that the boundary is contained in V prime, or phrased differently, the size of this set is, well, at most the size of this set. Okay, but then we just put things together and see that this is at most S over 2, and then we pick up the delta there. Okay, but this means that actually an immediate corollary now is look at the support. It's a union of S and T contained sets. So now we say that if V prime is not too large, and in particular, this will be the case if V prime, you should think of V prime as the neighborhood of a term. Okay? Then you know already now, like, how can I know that V prime is not larger than this? Well, if the degree of the term is not larger than this, divided by the overlap. Right? Which is, so that's where we're going to get delta S divided by 2L. Okay? So if the degree of T is less equal delta S over 2L, then the size of the neighborhood on the right is going to be at most delta S over 2. Then this lemma says that, well, if so, all SV contained sets are actually S half V contained, which means that look at the union. You can take the union of any two sets, and that union, a union of two S half NT contained sets, or any such union is S half plus S half contained, S contained, and then just by induction, I see that larger and larger unions here are in fact S half V contained. So in the end, by induction, all the support let me just see so that I write it. So the S support of such a V prime is in fact S half V prime contained. Are we happy with this? Question?
Yeah, so in lemma 3, there is nothing really special about S half, right? I mean, you could replace the S half in the upper bound on the size of V prime, and in the conclusion of the lemma by any S prime that is at most S.
I mean, yeah, but I can never. The special thing is that you can bring the size down to S half. You cannot bring it further down if that's. I'm not sure. Yeah.
I mean, if you would have a better upper bound on the size of V prime, then you could bring it further down, I think. If I.
Yeah. I mean, yes, sure, but yeah, and so, but this is So, but I want to allow. The reason I don't want V prime to be small, I want V prime to be as large as possible, because I want the larger I can make v prime, the better my degree lower bound is going to be. So this is a parameter that I want to maximize. Because if I make v prime smaller, then I'm just going to get a worse degree lower bound in the end. I don't know if that's...
Yeah, so that's an argument why you're only sort of interested in the S half case, I guess.
Yeah, I'm interested in being able to deal with as large sets as possible, and then I just play with the parameters so that there's always going to be, I mean, on all of these arguments, there's always going to be a factor 2 up and down. And I just want this, so there's going to be something and something divided by 2. And the larger I can push something, the higher up I can push something, the better degree lower bound I have. And so to optimize parameters, something will be the largest set for which I can guarantee expansion. Okay. So now consider a UV graph, UV Q graph, which I sometimes will call fancy style G. It's called fancy style G more often in the notes, I realize now. I haven't quite been following the notation in the notes always. Let T be a term. And suppose that U prime is is strictly larger than the support of T, but very happily, it's not too large. Then I claim that there is a P in U prime minus the support, and there is a V that lives in that is a neighbor. It's in the boundary of U prime, as witnessed by the fact that it is a neighbor of P, but it's not a neighbor of T. Like for any graph that we've defined, suppose that I pick something that is larger than the support, but not too large, then I can always find an edge to P. This is what we're saying here. Like, for instance, expanding this figure a bit with P5 and V6. This figure maybe. Let U prime now be actually, let me. Oh. Okay. So what I'm saying is now look at this blue set. Let this be U prime. U prime is not contained in the support. I'm saying there must be a reason for this. There is some P, happens to be this one, that has a unique neighbor that is not a neighbor of the green guys and also is not a neighbor of T. And indeed, here it is. So there has to be a set here that does not contain any variables from here or from T. And this is just a graph argument. So what is the proof of this? Well, note that, okay, so firstly, U prime is not S and T contained. Because if U prime was S and T contained, it would be inside this union of S and T contained sets. Okay, why isn't U prime S and T contained? There are two ways to fail. You could be too large, but U prime is not too large. Okay, so the boundary has to be outside. So we know that the boundary of U prime minus the neighborhood of T has to be non-empty. Okay, so fix a V inside this set and fix P to be the unique neighbor of V inside U prime. Okay, so since the boundary is not inside MT, there is a V. Fix it. It is a neighbor of some unique guy in P, so this is a complicated way of writing this type. So it's a neighbor of V and it's inside the boundary of, sorry, it shouldn't be boundary there. It should be just inside U, sorry. P is a neighbor of V and it is contained in U prime, sorry. Right, and I claim that this is what we want. What I need to argue now, so what have I done? So I think we're done with this. V is clearly not in the neighborhood of T. And it is a neighbor of P, and it is in the boundary of U prime. So we're done with that. Now I just need to argue, how do I know that P is not inside the support of the neighborhood? Okay, let me maybe argue this by picture. So here's the support. Here is U prime. And I have now V that is in the boundary of U prime, right? So it has a unique neighbor inside here. Suppose, and I want to argue that P is in here, but it's not inside here. Suppose that it was. Well, I mean, if it was, then this is the only vertex in all of U prime that has this guy as a neighbor. So in particular, it would be also in the boundary of the support. Yes? But the support of T is an SNT contained set. So the boundary of this set is in fact inside the neighborhood of T, which V is not. So I've argued by picture that indeed P has to be in U prime, that's how we chose it, but there's no way it could be in the support of T, because if so, the support of T would not be an SNT contained set. Now we are ready to do the heart of the proof lemma. Are there any questions at this point? So you can think about it. In my notes, this is now, I think I lost the numbering, but this is lemma 6 in my notes, the heart of the proof lemma. So the assumption is that G is a UV Q graph, as we have defined before. T is any term. And we're supposing that left-hand subset of vertices is containing the support, but is not too large. And now we want to argue that, well, if I reduce modulo u prime union q, this term t, then I get the same result as if I reduced only modulo the S support of t union q. One important observation here is that up to this point, I just argued about the graph, about the edges, about unique neighbors. We did not really play any games or anything. Actually, so we sort of just did the resolution proof more or less over again. So up to this point, if you think I don't know, I guess what I'm saying is that you can either watch this lecture again or you can watch, what was it, 2 lectures ago, because we've done the same thing. So, but at some point we have to start to use the goodness of the edges. And this is where we need to use the goodness of the edges. So my first observation is, let's argue by induction. It's in fact sufficient. I'm just going to argue that if u prime has this property, then I can remove one vertex from u prime and without changing the reduction. So I can find some vertex set P so that I remove P from U prime and the reduction doesn't change. Suppose I can do this, then I hope we all agree that by induction, I'll just take the sets in U prime minus the support and peel them off one by one until they've all gone away. I only need to remove one. Are you buying this? Okay, and of course we had a peeling lemma here that kind of suggests how we would do this. So we're gonna fix. Let me actually borrow to save typing. So we are in a situation where we have this P and we have this V, right? And let me also note for purposes of bookkeeping that I claim that I proved both of these properties, the second one by picture. So fix P and V with these properties. I'm going to use them over here. And we're going to do what we did before. Let's do the reduction modulo u prime. So t, when I reduce it, I'm going to write it as a part inside the ideal and then some irreducibles. Let's look at first. I take the polynomials inside capital P, this P. And I get something like, all of letters now are polynomials. So I get C sub P times P. And then let me work on U prime minus P. And I get some coefficient polynomials Cu times U. And I also have some polynomials in Q, CQ times Q. And then we have the irreducibles. These guys are irreducible terms modulo this large ideal. Right? This is just what happens. Like I look at T, I apply this OR operator, and it turns out that it does this calculation and spits out this. Are you with me so far? Okay. Now, let rho be a winning assignment on the edge PV. Note that PV is an edge in the good boundary. So this is a good edge. What do I know about rho? So let's carefully write down some properties. We've already argued some of them. So first, for all polynomials U here, it holds that they don't intersect V. Because if they did, there would be an edge coming somewhere from here to V. but all the edges to V are coming from here. And for the same reason, bars T intersect V is also empty, because if V contained a variable that was contained in T, then V would have been a neighbor of T, but it isn't. So this means that when a row is this assignment, it's an assignment to V, it will not affect any of these polynomials. It will not affect this polynomial. Sorry, it will affect these polynomial. It will not affect these at all. It will not affect this at all. Let me say that again because I screwed up. Whatever I do to V, it won't change T because T doesn't contain it. Whatever I do to these U polynomials in U prime minus T, it won't change it because of uniqueness. It will hopefully change these polynomials in some good way, like I'd like to remove them, ideally. It will affect Q, and I need to worry a little bit about this. We'll talk about it. It will affect R, but I won't be worried about this because what happens when I take irreducibles and hit them by restriction, they remain irreducibles. And I'm going to be happy with this. So the key property is that once satisfier has played the assignment on V, we know, what do we know? Again, let me write this down. We wrote this before, but when I play the assignment row, I either satisfy polynomials in Q or don't touch them at all. So note that Q restricted by row is a subset of polynomials. It could be anything in general. It turns out that because of how row is structured, it is a subset. This is not true in general, but it's true for us because row is the strategy in a good game. On a good edge. Okay. Furthermore, it is not possible for the adversary it is not possible for the adversary to find an alpha that satisfies Q and falsifies P restricted by Q. Right? So, phrased in another way, Q implies P restricted by row. And now we're going to use this thing that I said that, well, this means, since we're in a multilinear setting, that in fact P restricted by row is in the ideal generated by Q. Okay, which means that P restricted by row, I can write that as C prime Q for polynomials. Again, all the coefficients that you see now are polynomials, important, times Q for Q in Q. Lowercase q and uppercase q. This is true since row is a winning move. Now we're starting to use the property of the edges. Are you with me so far? Because now we're done, almost. Now we just need to piece things together. Okay, let me call this dagger. And now I'm going to write a double dagger. Let's see if we can fit this. So take a dagger and hit it with row. Okay, and let's see what we get. T doesn't change. P changes. I get P restricted by row here. So I will actually from for every polynomial in here, I will be able to write it on this form. So just by telescoping all of them, P gets replaced by some, these are other coefficients now. Maybe let me do them double primes. Right? P restricted by rho, all these polynomials, I can rewrite them on this form. So this takes care of the whole set capital P. Fantastic. What happens to you? Not much. Well, CU, I don't know. I mean, that can be whatever. But the important thing is that these guys are not affected. Okay, and then what happened with these guys? Well, it's still true. Some of them might vanish, but I will get for all Q's in Q restricted by rho, and this is a subset of Q. I will get CQ restricted by rho times Q plus the irreducibles are K, and here I really don't know what happens. Rho might do anything. Okay. And now I claim that, okay, so let's look at these guys. They are irreducible modulo already this ideal. So they're definitely irreducible when I remove P. So these are irreducible for both ideals that we care about. And here I have written T in this lies in the ideal generated by U prime minus P union Q, right? Actually, maybe another color, maybe orange. So U prime minus P union Q, this ideal takes care of all of these guys. Right? So this lives in this smaller ideal, but also in this larger ideal. So now I've written T, this expression is actually rewriting T as a sum of irreducibles in this larger ideal plus a polynomial that lives in this larger ideal. So by uniqueness, this thing that we have here is actually what this thing was all along. But clearly, so in particular, we have that summing K, RK over rho, that's exactly the same as RK. But note that what can I say about this sum of RK over rho? Well, these are irreducibles living in the smaller ideal. These are irreducibles modulo the smaller ideal, and this lives in the smaller ideal. So this actually has to be by uniqueness, the R operator, what the R operator spits out for the ideal U prime minus P union Q. Okay, so now I've shown, hence, what's the punchline? Well, the punchline is that the reduction modulo U prime union Q of T, which is what we started with, turns out to be equal to the reduction modulo U prime minus this set P of polynomials union Q of T. And now by induction, we're home. Okay, we have a few minutes left. We'll try to not waste too much time. Are there questions on the heart of the proof lemma? Like this is, I should say also that here we used properties of the special graph that we built, but this heart of the proof lemma, one version or another of it appears in all polynomial calculus lower bound. So this is like basically you have to find some kind of ideals here so that you can do this part of the proof lemma. And we just built it with the graphs. We'll see. For one thing you can think about is for graph coloring, we don't know how to build a good graph with nice edges. But I don't think we will have too much time to talk about it. I could also say for any locals who have had who have logistic responsibilities or who have already had enough spiritual nourishment and want some other cake nourishment, then I guess it's okay to leave if you do it discreetly. I'll try to wrap up as soon as I can. Okay, just a few more lemmas. The first one is that, well, if the degree of a term is not too large, then the support of the term has size at most s over 2. Okay, and this is, again, we kind of did this already. The point is that, look at this term, the neighborhood of t is, well, every variable can contribute. So here, since we're looking at a term, the degree is actually the number of variables. So the number of variables in t contribute to edges. How many different v's can every variable occur in? At most L. And now we just say, okay, what was the degree? Well, you promised to me that the degree was delta S over 2L, and the overlap is L, and now we're done. Okay? Because we said that okay, so that means that the neighborhood of t, let's write it down, sorry, is at most delta S over 2. But then we just proved a few minutes ago that, well, if a V prime set on the right had at most this size, then all SV prime contained sets actually had size at most S over 2. So then we get this. So in the notes, this is lemma 3. There's a kind of a boring lemma that, let's see if I will do it or if we'll just hand wave it. I claim that one thing that you can worry about is when you start reducing, you might pick up new variables. Right? I start reducing modulo a set u prime, and now I can be concerned that, note that the filtering set Q contains any variables in the whole universe. And if I start picking up tons of variables, then I lose control and my V prime sets will be too large and this bound won't apply and things will crash and burn. So I claim this is not a problem. Take any left vertex set U star and any term T and think about what happens. Like, look at the polynomial that is spit out when you reduce modulo U star union Q, where Q contains all variables in the whole universe, potentially, it usually will. So reduce T. And the question is, what can my neighbor set be like now? And I claim that, well, this is going to be, I will only get neighbors of U star plus neighbors of T. Okay. So proof, well, let R be this polynomial. That is, T is Q plus R, where Q lives in this ideal, R are irreducibles. Take any V on the right, such that V is not a neighbor of U star, and it is not a neighbor of T, then I want to argue that V can also not be in NR. So here I will use, when we built the graph, we had a property on edges, but we also had a property on all the right-hand side vertices. We said every variable set V, it was possible to set the variables in some way that respected Q. So this was not a property of edges. This was like a property even of right-hand side vertices. So there is a row V assigning these variables such that Q row V is contained in Q. This was by construction of the graph. And now just look at T restricted by row V. Clearly that is equal to Q restricted by row V plus R restricted by row V. But now V is, by assumption, it's not contained in T. So this T restricted by this guy is just T. And note that since rho is zeroing out things in Q or leaving them unchanged, this actually still lives in let's see. So these variables, let's Q is now living. I should write this down. So Q, this Q lives in the ideal generated by U star and Q. Okay. So since rho is assigning a vertex at V that by assumption is also outside of U star, clearly nothing in here is affected. Rho might affect Q, but we know that it just zeroes out all variables that all polynomials that it affects. So this guy actually lives also inside U star union Q. Okay, but now I've written T as another polynomial inside this ideal plus R restricted by rho V. Okay, so by uniqueness, I know that R is the same as R restricted by rho V. But now note that if R actually contained any variable in V, then these would be distinct. But they're the same. So this proves that, this proves, sorry, I had a typo. This proves that V indeed is not in the neighborhood of R. Okay, so now there's one final lemma, and if we can prove this, then we're actually done. Remember, there was one magic step. There was this magic step that said that I had xt prime for t prime in the reduction of t, and that I can somehow just substitute the reductions. Let's write down exactly what this was, and we'll do it, and then we will be done. This is a better marker. So this is the final technical lemma that heavily uses the heart of the proof lemma. So suppose that the degree of t is not too large. The upper bound that we have is delta s over 2l. Let's round that down. That's our degree bound. T has strictly smaller degree than this, so that I have room for multiplying. Then, if for such a t, I claim that for any t prime that is in the reduction modulo the support of t union q of t, that, right? These were the ones we had when we were dealing with multiplication. And any x that is not a variable in t, because we're in a multilinear setting. So, I mean, if x is a variable in t already, then multiplication is not so fun. Then I claim it holds that the reduction modulo the support of xt prime union q of xt prime is equal to the reduction of xt prime where I plug in xt instead of xt prime, right? This is what we used, and once we had this, we were done. Okay, so now our plan, we want to prove two things. We want to show that sup, the support of xt prime, is in fact contained in the support of xt. And we want to show that the support of xt has size at most s. If we can do this, then we just apply the heart of the proof lemma. Let's say, what's the heart of the proof lemma says that this is what we're interested in. So this is our support. We reduce modulo something larger, apparently, but not too large. Then the heart of the proof lemma said that these two are the same. So this is like really the only thing we have left now. Okay, we are immediately done with this because of this lemma. Because the degree of xt is not too large. So we need to work on this. And this turns out to be a little bit tricky, or at least I don't know how to. It's a little bit of a roundabout argument. Let me see if I can quickly do that argument. I want to show that I don't have a good handle on this, but I will show that the support of xt prime union the support of xt is S and xt contained. So note I only care about this set, the support of xt prime, but I don't know that that is a contained set, but I'll take it, I take this and the union of the support, and that will tell me, like, suppose that this is an xt contained set. Well, the support is the union of all such sets, so then I will have proven that the support of xt prime union the support of xt is contained in the support of xt. And then in particular, well, if so, then this is definitely contained. So a little bit funky, but so basically I claim, suppose I can prove this, then we're done. Then the lemma follows. And then we're actually like done with everything. Are you buying this? Because then we just apply the heart of the proof lemma. So observation, for any t prime in this reduction of sup t union q, any t prime in the reduction of t, I have, just by the way reductions work, when I reduce, I get smaller things. So any t prime is smaller than t, which in particular means that the degree of t prime is less equal to the degree of t. Therefore, by lemma 7, what do I know? Well, I know that the support of xt, this I already knew, was size at most s over 2. But since t also has small degree, the support of xt prime also has size at most s over 2. So this means that this set has the right size. So all I need to show now is that the boundary of these guys are contained in NXT. And this is where I'm going to need this. Okay, so we need to show that the boundary of the good boundary, the respectful boundary of the support of xt prime union the support of xt is contained in the neighbor set of xt. Now, by lemma 8, this says, lemma 8 says that, well, the neighborhood of this guy can't be completely crazy, right? Lemma 8 says that the neighborhood of t prime is contained in the neighborhood of the support of t union the neighborhood of t. So u star is, for u star, I plug in the support of t. Okay. Now, I also know that the support of t is clearly inside the support of xt, because this is a larger, has a larger neighborhood than this has. So if I just combine this, I get that the neighborhood of xt prime is the neighborhood of x union the neighborhood of t prime, which is inside the neighborhood of x union the neighborhood of the support of t union the neighborhood of t, where I'm using this. And now I just collect and say, well, since this support is inside this support, then this means that this is all contained inside the support of xt union the neighborhood of xt. Okay, so now I have a handle of the neighborhood of this new term that I don't quite have a good handle on. Okay, so now we're almost done. Let's look at the boundary of the support of xt prime union the support of xt. So that is going to be, first, let me take the boundary of the support of xt. The contribution, I take the boundary here, and clearly anything in that boundary, I mean anything that lies in the support, in the neighborhood of the support of xt, is no longer unique, right? I take anything in the boundary here, but then remove something that is in the support here, then it has at least two edges. So if this measures the contribution of this part of the boundary that survives. And then suppose I get, from this, I just take the whole contribution of the boundary. Okay, again, the boundary of this union is, let's take everything in the boundary here, and let's suppose it survives. Let's take everything in the boundary here that is not neighbors of these guys. Okay. Let's keep working. So now I actually know that, well, the boundary here, a very optimistic estimate is that it's everything. What do I know about this? The boundary of the support of xt. Well, this is an xt contained set, so I know that this boundary is in fact in NXT. Right? This is a contained set, so this is fine. And now let's see, what do I know about this guy? Down here, I know that that is contained in the neighborhood of the support of xt, union the neighborhood of xt. Let's look at this guy. That's what I'm removing here. Okay, so once I've removed that, what do I have left? nxt. So this gets me a contribution of the neighborhood of xt this gets me a contribution of the neighborhood of xt. Taking the union of the two, I hope we can agree, even though it's late in the day, that I get the neighborhood of xt. Okay, but this shows that the boundary of these guys is in nxt. So this, and it had the right size. So indeed, I've shown now that this set, it had the right size. The boundary is indeed contained in nxt. So this holds. And so in particular, if the union is in the support one, then definitely this guy is in the support. And now, okay, what do we need to do? Now we need to prove that, now we're ready to do the proof that this is a pseudo-reduction operator, but we almost did it. So let's see, let's recap. So I need to argue that 1 doesn't reduce to 0. But this is the same proof as for resolution. Again, we actually did this, that the support of 1 is small. Hence, by appealing argument, the supporting set has to be satisfiable, and 1 doesn't lie in the ideal of a satisfiable set. And also 1 is the minimal element with respect to the order. So we actually know that R of 1 is 1, which is not 0. The fact that multiplication works was exactly this lemma was the magic step, if you remember. Okay, so now we've done the multiplication. The only thing we haven't done is, well, if f is an axiom in the input set of polynomials, and so what was the condition? Okay, maybe I'm going to say something. I don't think we have the energy. I think it's getting too late. And maybe we don't have the energy to do this. Let me just very, very quickly try to say something about this. So what was the condition? So f is a polynomial, and we had actually the technical condition, if you remember, or maybe I forgot to state it. So f is an input polynomial, and we had this condition actually in polynomial calculus that it doesn't contain ridiculously many variables. In fact, it contains at most this many variables. So what I do now is I just say, okay, let me construct a bogus term. Look at all the variables in f and multiply them together. This gives me a term t star. Note that t star doesn't have too high degree. So t star, the support of t star has all the nice properties that in particular, we know now that the support of t star has size at most s over 2. It's also not hard to see that for all the terms that actually are in f, we have that the support of t star is clearly containing the support of t, right? Just because there are more variables here than in here. So anything that is contained with respect to the neighborhood of this is contained with respect to the neighborhood of this. Okay, but now there are like, basically now I just need to use the heart of the proof lemma, because reducing, so the R of f is gonna be, I'm gonna do this a little bit sloppily. Basically, I'm gonna look at all t's in f, reducing t. By definition, that's going to be sum over all t's in f, reduction modulo the support of T, union Q of T. Now, by the heart of the proof lemma, T star is a superset of this, but it's not too large. So actually, I'm going to be able to write this as reduction modulo the support of T star union Q, T. Okay, and now by linearity, this means that this will be the reduction modulo the support of T star union Q of the sum of all of these guys, also known as the axiom F. Okay, so now this is by the heart of the proof lemma. So here, so now I'm reducing F modulo the support of a term that contains any variable in F. T star contains like all variables occurring anywhere in F, and then we take the support of that. And basically what I need to argue, but I think we should wrap it up and you'll have to read it in the notes, that now I just need to argue that, well, it could not possibly be that, basically I want to argue that one of two things will happen. Either the Q set, either the filtering set actually implies F, which is kind of a weird special case. But if it doesn't, so what I'm worried about is, suppose Q does not imply F, because clearly if Q implies F, we're done. And now I'm worried about that there is a variable set. So I'm worried about, okay, so where does F live? F lives in some P, some vertex. And I'm worried about that, maybe there's a vertex set in NP, in the neighborhood of P, minus the neighborhood of T star. Because clearly, what I want to argue, suppose that F lies in P, then I want to argue that P is an S and T star contains F, right? If I can argue F lives in P and this singleton set P is S and T contained, then it lies in the support and we're done. The only way this could fail is if there is something in P that is outside of T star and is in the boundary. But if so, PV cannot possibly be a good edge. So any such V does not result in a good edge PV. So that shows that this set is in fact S and T contained. So it lies in the support and we're done. Okay, so this gives us now, finally we're done. This gives us a lower bound on almost all polynomial calculus degree lower bounds that don't depend on the field characteristic. This does not give us a way. So one open problem that would be nice. Can we do anything like this but incorporate dependence on the field characteristic? Alekhnovich and Razborov has one way of doing this, but it doesn't generalize to this setting, and it seems hard. There are also other problems for which it seems that they are not so nicely structured so that we can build an object like this where there's not too much interaction. So in particular, I don't know how to build a UVQ graph for the graph coloring problem. So we do have lower bounds for graph coloring. We will need like a heart of the proof lemma for graph coloring for an appropriately defined support, or what it's called in that paper, I think, closure for graph coloring, but I don't know how to do it in this setting. And that concludes today's lecture.